All right. Good evening, everyone. Ashoten, Evergreen Valley College, and here we are on chapter 14. Uh, Chapter 14, Cosmic Samples and the Origins of the Solar System. So basically, it's a chapter that focus on one of the subjects I put in one of the discussions, uh, chondrules and these little pieces of material that were formed in the very beginning of the solar system. So to get information about this um, relic, it's important because we can figure out the conditions upon which the solar system was formed. I was don't believe in everything that is in the internet, especially in YouTube, but I think this is reputable. This is not a fake thing. I don't know if this is fake or not, but yeah, so this I don't know. But if a meteor hits your car, I don't think the insurance will pay, but you can make some money. You can sell the story, and that might be somehow important. Oh, we have Jasmine today. Look at that. See, the number of people are growing. That's amazing. We
Act
have,
of God.
oh yeah, or the meteor, something is communicating, it's coming by. All right, so let's get serious here. So basically, when the solar system was formed, and let's just remember the details. I know this might be pretty much simple and clear for some of you or most of you, but a star formed out of gas and dust that exists in a galaxy. And later on, we are going to learn that galaxies, they are called spiral. They do have cold gas, and cold gas is an important ingredient for star formation. Um, Elliptical galaxies, for instance, they lack cold gas. They have gas, but it's hot. And cold gas is important because when gravity kicks in, given a certain density, gravity kicks in and starts to pull in this gas to the point that a star system is formed. In addition to gravity pulling in, gas also happen to be going around the galactic center, and so rotation is an ingredient in every single component of this giant molecular cloud. Um, and when contraction takes place, then the Ballerina effect also takes place, and this rotation is spins up, and as it does, if you apply the laws of physics and laws of conservation of angular momentum, what you're gonna find is a gas that happen to be at certain distance and angle from the center part of the protostar is supposed to be formed. This gas will prefer to fall towards the equatorial plane and then spiral inward towards the central star. So when a star system formed, it forms in association with a circumstellar disk, pretty much circumstellar gas disk. And uh, since the laws of physics in a micro universe are the same in the big universe, the process is basically the same that govern formation of galaxies. So galaxies are not just a gas that is going to form a star system, but it has enough gas that it will form hundreds of billions of stars, but the shape of the galaxy in spiral galaxy obeys the same rule. So you have a contraction towards the center part of the galaxy, and then you have this flattened process that gives rise to spiral galaxies. So gravity, angular momentum conservation, and voila, you have a new star system, or you have a new galaxy. Now, out of this circumstellar disk or circumstellar gas that goes around the star, then you have another process going on. Now you have a life of its own there, because the first major process that occur is when static forces, probably the same process that leads to the formation of a snowflake. So up in the atmosphere, you have the proper condition for grains to be formed, either because you have some seeds upon which the ice can be formed, could it be pollen, could it be some aerosol, and and then static forces will start adding one molecule at a time, and then eventually you have a snowflake being formed, and we call that process accretion. Is an accretion which is the process by which the mass keeps just growing because some force is pulling things in. Um, so this accretion happens in the disk, and then grains start to be formed, and these grains will stick together. Again, it's static force, probably the same process that leads to have the back of fridge, the back of our TV, especially the old TV with the cathode ray tubes. Probably not so much the TV nowadays, a different technology. So the electrostatic forces stick dust on the panel on the back of these appliances, and then you have to clean, otherwise you might initiate some fire or something, and your appliances will not work properly, as I discover in my dryer. I have to open that thing and clean it up. But basically, although that is a different process, but in the circumstellar disk, all these little grains start growing in size, and then eventually they become what we call planetesimals. So planetesimals, they range in size from few centimeters all the way to miles in extent. And as they circle the sun, they collide, they coalesce, and they grow in size to the point that eventually they will be big enough to have gravity of its own that it can attract now objects from its neighborhood. So now you have accretion again going on, but it's an accretion driven not by electrostatic force, but by gravity, basically. So now these you could call protoplanet, they are big enough so that accretion can drive the gas and particles towards this protoplanet. And then you have a planet formed like Jupiter with a system of moons going around. Probably Jupiter was formed in a way very much similar to the way the solar system itself was formed, except Jupiter has much less material. So let's start with the definition of meteors. So meteors are any piece of junk that happen to be out there in the night sky. So meteors, or in fact, if you want a more general terminology, meteoroids are pieces of rocks or debris that happen to be in space in the interplanetary space in our solar system. Now, some of these meteoroids, sometimes they hit our atmosphere, they penetrate our atmosphere because of gravity force. Earth is attracting them. In a given year, Earth grows in mass. Earth can grow, and the calculations are complicated to be made, and there are lots of uncertainty. But you can see claims here and there of about 30,000 to 100,000 tons of material that falls on Earth every year. So is Earth getting bigger or more massive every year? Probably yes. But Earth also loses material. Earth is there are unstable atoms on Earth interior, and these atoms lose energy. It's called radioactive decay. They 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 are unstable and they break down into more stable atoms. And by doing so, they release energy. In fact, that's one of the major sources of heat that we have in our interior or Earth interior. And then eventually, this energy escapes Earth, and therefore Earth becomes less energetic or less massive. Um, but Earth also, in the upper atmosphere, Earth is losing a lot of hydrogen and helium and can be significant. 80 to 9,000 tons of this gas is being lost every year. The sun's radiation breaks down hydrogen molecules, and this hydrogen escape. They just go away, and pretty much the solar wind pushed this away to the regions where Jupiter are. So you have a give and take on Earth. But meteors, when you see a shooting star or something cruising the sky at night, this is a piece of debris. It's not a star that is falling. Stars are big, right? So it's just a little piece of grain, can be as big as a bin, like a black bin, and as it penetrates the atmosphere, and because of frictional forces and drag forces, in fact, it warms up, and then it gets hot, and then you have this trace that happen in the atmosphere, and sometimes the amount of mass and pressure becomes so intense, the particle itself can explode in the atmosphere, can create some explosion there. Meteor showers, as comets, meteor showers happen to be associated with comets. So when comets approach the sun's radiation and solar wind happen to evaporate and to liberate particles that happen to be trapped in the comet body itself. And because of the heat, these particles are released as the comets go away. Now, so in fact, you have a path of death as the comet go around the sun, and this path is there, it stay there forever. Now, if so happen, if Earth goes through that path as it goes around the sun, you might see lots of these debris falling on Earth in a given region, which is the region where Earth happened to meet this path on a certain time of the year. And this is very consistent. It happened because the path is fixed in a given location, and Earth goes through that path, through the region every year, and then as it goes, you have this major shower coming in, and that is called meteor shower. And then you have several particles that can can cross the sky. If you happen to observe them, and if you happen to keep track of their directions, you can trace down to a point, and that's the point where usually associated with a constellation. Constellation, as we saw previously, is not a group of stars, but is a region in the sky. So Leonids is a meteor shower that happened when that, as you see it, it happened to be in the direction of a constellation Leo. That's why it's called Leonids. Oh, then you have a whole uh, table with their most common time that you can go there and observe them. Now, do you need a telescope to observe those meteor showers? Not really. Telescope doesn't help unless you wanna do something exciting, which is very difficult to do. Is to place a, since we are trying to get a spectrograph. Some people try to get a spectrograph of meteor shower, which is you have to be very lucky. You have to have your telescope point in a given direction, expecting that a meteor is going to hit the field of view of your telescope, which you know is very small. Is one arc minute or 2 arc minutes. It's not that big at all, and you have to have this meteor tracing being bright enough to impress your spectrograph, and then you can take a look and see if you can detect some exciting ingredients in that particular meteor. Some people do that, and they really try, and it's a cool thing. That's another trace over there. And meteor shower. Now, when these debris they hit the ground, uh, then you collect them, and then you can call them not a meteor, but you call meteorite. So meteorite is one of these debris. I think is the next one. Is one of these debris that hit the ground, and then you collect them, and then you can analyze, and then you can figure how they were formed and what sort of ingredients they have, if you can analyze them uh, more in detail. Meteorites, some of them are stony rich, which means pretty much rocky type. Some of them are metal rich, so they have more a high content, higher iron content, and those with a higher iron content can be easily detected with a metal detector. That's how they found it. And the stony type of meteorite are a little bit more demanding to find, because you have to, first of all, know where to look for them. And you cannot use a metal detector to find them. And as you locate them, you have to be able to differentiate them from some of our Earth rocks. They're probably subjected to some erosion, so you have to be able to distinguish those two. Antarctica is a nice place to go, since if they hit the ground, you can send now drones, and then the drones just fly, on top, and then with the camera you can find mine or micro craters formed by the impact of these meteorites in Antarctica, and then you can go there and collect them. It's not a lot of rain there. Glaciers move. That's all right. But that's that's interesting. A seat cushion and/or my cane chair. Again, you can make it. I mean, you can sell this in eBay and make good money. Rick could sell his NASA little thing in eBay. Somebody would buy it. Okay. Uh, those are some of the types. You can see some of the minerals. Some of the minerals that were formed in the circumstellar disk itself, and then you can classify them. You can do analysis. You can do spectroscopy, mass spectroscopy, and determine what they are made of. Olivine crystals. Olivines is a crystal that can it's primarily formed in earth mantle. It requires uh, high temperature, about 1800 Celsius, to be formed in earth mantle. But they can also be formed in the circumstellar disk if they are exposed to ultraviolet radiation from the central star itself. These young stars, they are not relaxed like teenagers. They are pretty wild, and they can get pretty wild sometimes, and they go through process of um, flaring, and the gas of the disk also, as it falls in the star, creates hot regions that can in its turn produce lots of ultraviolet radiation, and this floating of ultraviolet radiation going through the disk can create olivines, and then olivines can be trapped in crystals, and then later on you can analyze them. But the main point is, you can once you collect this material, you can kind of infer the properties of the circumstellar disk that formed our own sun, or solar system, better saying. So differentiated, we learned this word differentiation previously. Pieces of planetesimals in the circumstellar disk that happen to be big enough to undergo a entire melting, which means they become liquid at certain point in their trajectory, at certain point in their life cycle. Once they melt completely, differentiation or chemical differentiation occur, and basically um, the heavy iron nickel content sink to the center of mass of this melted material, first of all, and then the lighter material, the rocky type, stays floating on top. And if it's big enough to host an atmosphere, then the atmosphere stays in the very external shell. And, and that's why uh, big objects in our solar system tend to be spherical because they melt at certain point. Um, and like Vesta, for instance, is slightly circular or spherical because of this melting that occurred previously. So when one of these objects that happen to be differentiated, they collide, they so when they collide, you might have pieces of the mantle alone casting away and become meteoroids in the solar system. So they are primarily stone. But if part of the core that is iron rich also becomes a meteoroid encircling the sun, and if you happen to grab them or to find them, is pretty much pure iron. So these different type of pieces that one collects can tell a lot of the family that produced this debris. Um, People studying them, called doing planetology basically, they study these pieces not only by their dynamics, which means if you can trace with precision the families of these pieces, so where they go, and if you could trace down millions of years, hundreds of millions of years, and to the point of the grand bombardment in 3.8 billion years ago, if you can trace and go back to that time, where all these pieces of debris were located, could you do that? And so that's the dynamics aspect of this study. So you try to find which major planetesimal, once broke, gave rise to this family of pieces that you studied. So you know the families, and you can trace down the origin to a bigger planetesimal. And another type of the study is to find the family um, based on their chemical composition, the chemical signature. So a piece of rocks, they might have similar um, chemical composition. So if you break that in pieces, so the pieces should have similar composition, which means they were formed at the same location in the solar system. So depending on how far they are from the sun, they're going to have more or less metal oxides. They're going to have more or less carbonates, more or less silicates, and then by doing so, you can trace down pieces of debris scattered in around the sun, and bring them to a common origins based on their chemical composition. So we can use either dynamic, or you can use also the chemical aspects or chemical signatures on it. Okay, let's go to the next. And finally, formation. When this is, I think these pictures tells everything. So you gotta have some giant molecular cloud over there that fragments into smaller clumps, and these clumps then become subject to gravity that will govern the process of contraction. But because they are not just floating in the space surrounding the sun, but they also might have some initial rotation. So when this contraction takes place, the contraction leads to the formation of this flattened structure, which is a circumstellar disk. Now, out of the circumstellar disk, conditions will be such that crystallization and grains will start to be formed and grow in size, and eventually you have planetesimals. So these planetesimals will be of different chemical composition. Those closer to the sun will be more metal rich than those formed further out. They will be more ice rich and more populated, more with a larger percentage of volatiles, and that's how it goes. So being closer to the sun, and the sun is the big element controlling everything else. Like when we study galaxies, we will see the core of the galaxies have a black hole, and more is finding the black hole controls not only the dynamic of the bulge of the galaxy itself, but also the dynamics of it, the different types of rotation and orbital motion the stars in there go through is all controlled by the center part. And the sun is not alone. I mean, the sun, because of its heat, it controls the chemistry of all these objects closer to it. So any object that is formed close to the sun is going to be more rich in metals. And as you move away to the point where, for instance, the sun is, I mean, the earth is, then the percentage of metals diminish because the sun itself has swept away all these volatiles to the regions where these giant gas type of planets are located. Pluto is there. I don't know why. It's not a planet. Probably this is an old picture. But see, metal oxides, that's the high temperature. With this high temperature, you cannot have water, ammonia, and methane. So those are pretty much concentrated in the region where these Jovian planets happen to be located. Now, the solar system is then segregated into two major types of objects. Um, the terrestrial planets or terrestrial objects, including Mercury, Venus, Earth, Mars, and the asteroids. And also includes Earth, Moon, and Mars, moons, Phobos, and Deimos. Looks like asteroids that have been captured from the asteroid belt. So if you take the asteroids Mars and its moons, Earth and its moon, Venus and Mercury, then you are talking about terrestrial objects. And as terrestrial objects, they are rocket type. They might have like Earth and liquid core, but this liquid core is not water, it's not methane, it's pretty much melted iron nickel alloy. And as you go to the regions further out, and this is not in scale, right? This certainly is not in scale, like distancing in miles or kilometers, not in scale at all. So in that region, this low temperature, the sun is pretty much further away. The solar radiation and heat is not predominant in this region. So primarily the volatiles are predominant in there. And then you have sometimes they used to use the books in the past used to employ the word Jovians. Jovians because they resemble Jove, which is Jupiter, right? So, but now some books called gas planet or giant planets or frosty planets, although most of their interior is liquid, basically, liquid nitrogen, especially in Jupiter. Now, looking at terrestrial planets, they don't rotate fast, they don't have strong magnetic field, and they don't have a lot of moons. When you look at the Jovian planets or gas giant planets, they rotate fast. They have several moons, and uh, and they have core, a rocky core. That's all right, but they are not of a solid surface. Their moons might be of a solid surface, and especially Jupiter Io is a moon that is pretty much active and full of volcanoes, and volcanoes spewing uh, um, uh, pyroclastic material, not so much different from what you see in pyroclastic volcanoes here on Earth. So that is the region of where the Jovian planets happen to be located. Now, comets, um, I mentioned asteroids. Comets are uh, the equivalent of asteroids in the volatile volatile and water, methane, and nitrogen type of ingredient type, more icy type, and they do have grains in it, and they happen to be concentrated in two main regions. One is called um, the Kuiper Belt, and the Kuiper Belt is a donut shape. Let me see if this is our solar system, the Kuiper Belt would be a donut shape going around this circumstellar material, and it's pretty much filled with a comet-like objects. And Oort cloud, WORT cloud, is surrounding the entire solar system in a spherical way, and is located 50,000 or more astronomical units away from the sun, and is also a source of possible comets in our solar system. Now, planetary system. There is only one in our solar system, and the answer is no. Um, Stars with circumstellar disk have been found out there, and is very much common. In fact, what we call EVC CSI, um, which is evergreens, a group of people interested in doing all kind of things related to science and astronomy and physics. And one of the groups is studying um, the interaction of this type of disk with the stars that are still in the process of formation, called T-Tauri stars. And they do have disk, and we can observe the interaction of disk with the stars. So this is a phenomenon that is happening as we speak. Our galaxy, technically and based on statistics data, our galaxy form 10 stars per year. That is the rate in which stars are formed in the galaxy, and is a process, is an ongoing process. And um, since there are circumstellar disks, certainly there will be exoplanets out there, and that is another section in our course, which is to explore the characteristics of these exoplanets. So exoplanets come in all sizes, shapes, and forms, and the smallest ones seem to be the most populated in the galaxy, and that's gonna be in another section to explore. but it's there. I mean, it's um, these circumstellar disks can be mapped now. Of course, this is not, this is a rendering image of what that might be. But part A is a is a radio image of um, what a protoplanet disk around this star would look like. So you have all these gaps, all these dark regions in there. Now, a bit of statistics of exoplanets, and it is found that based on statistics alone, most of the exoplanets out there are of Earth size. So if you look over here in this, in fact, it's more between Earth size and um, and it's called super Earth. It's about 2 to 3 Earth radii. The first exoplanets ever detected, the technique used was Doppler technique. Um, so astronomers were using Doppler technique and mapping the star wobbling motion as a result of being pulled by a Jupiter-sized planet, a large planet that happened to be close to the star. Um, so the technique was primarily spectroscopy. Now, with the launch of Kepler satellite, which is probably about to die now, um, it seems to be going in its last moments alive, if we could use that word for a satellite, is still collecting data. Um, then Kepler came and was able to uh, use photometry by and identify a different population of exoplanets, those very tiny ones, going in front of the stellar disk. So when the planet passes in front of the stellar disk, it diminishes the total brightness observed, and then you can infer properties about this exoplanet. So and here is indicating most of the planets found. Uh, the smaller size planets start to be detected once Kepler came in after 2010 or so. And the very first exoplanet detected, they were big, large, hot Jupiter closer to the star. It's called hot Jupiter because the idea is these planets are formed further out, but they migrate because they interact with the disk. They lose energy and then they spiral inward, disrupting the disk itself and probably planets that might exist inward. And then eventually they locate it and they settle closer to the star. Um, Now, once the planets are formed, let me go. Once the planets are formed, then they just go through their natural evolution, and then and that evolution implies cooling down, so they are becoming cooler, and they might or might not undergo transformation. So Mars went through severe transformation, and then you can see volcanoes in Mars, and Mars probably had all indication of having waters and oceans in its very past, and now all of that is gone. Probably Mars' atmosphere was not retained by Mars' gravity force and then pretty much escape. As I mentioned in the very beginning, Earth is losing about 100,000 tons of hydrogen and lighter volatiles every year, and so Mars, with less gravity, would lose even more, and then eventually all these light gases, hydrogen and water, what is hydrogen and oxygen, they would pretty much escape. Um, so Earth is geologically active, and its surface is being redone as we speak as a result of erosion and also plate tectonics that resurface and change the surface on a constant rate. And I think we have a chapter, an upcoming chapter, in which we are pretty much looking at Earth as an active object. If we didn't do that before, probably we did that before. Yeah, Earth as an active, geologically active object. And I think that's it. Um, that's Olympus Mons in Mars, the tallest volcano in the solar system. Uh, Probably because of Mars' low gravity, these volcanoes just grow immense. Um, and also is a result of a hotspot on Mars, so that's just keeping feeding the volcano, and the volcano grow in size, um, and became the tallest one in the solar system. That's it, folks. Uh, I think further down, it's gonna this this course I don't go in details, or I don't offer a lot of detail, and I don't spend a lot of time detailing characteristics of each object in the solar system, which was the main point of course we had Astro 14. It's pretty much solar system stuff, and then you'd go and study in detail each one of the planets, observations, aspects of each one of them. So we don't do in Astro 10. Astro 10 we present them in general, and then just to give you an overview of um, all the different aspects of objects that you can find out in space. Okay. Very good then. We're gonna try this Wednesday. We will try this EVC CSI, Citizen Science Initiatives. If you guys are interested, just let me know and I send the link. We're gonna try to connect again if we can, um, and then move on and get exploring this beautiful science with real data.
So,
Yes.
the one thing is about that. Remember, we had a little. I think was it homework or a discussion with the chondrite?
Yes.
Is that like part of that Bennu meteor?
It should yes, because when you collect pieces of it, you can then find the origins and find the ratio of a certain isotopes. You can determine if, in fact, that was part of another
Ye-
extra credit or so.
Yeah, extra credit.
Yeah,
Yeah.
you can find if the sun was formed with a companion or not, and if that companion exploded or not, and depending on the type of the ratio of certain isotopes, you can infer the temperature of this companion. So there are lots of rich information you can collect once you bring this material back to Earth, or if you can analyze this material up in space.
Yeah. Yeah.
Yeah,
Okay. So basically, that's different than the planetesimals material.
the planetesimals.
Yeah.
It's it's uh,
It's different,
it's
the material
I mean
that they're made out of.
planetesimals are hypothetically were the beginning of everything, right? The beginning of our um,
Solar system.
the planets and the moons, not the sun. The sun was pretty much in the
Already
center of
there.
mass, was already there, and pretty much casting radiation, and then eventually the gas start coalescing into this little material, and then these grains grew in size. These chondrules, they just keep on growing, and depending on where they were formed in respect to the sun, they would have certain composition, and then eventually they become big enough, and then we call them planetesimals, and then planetesimals might grow even to the point of becoming seeds of planets, and then we call them protoplanets. So this
Okay.
that's the hierarchy we use as hypothesis. There
So
is a
the
yes,
other one that I was talking about, the chondrites,
yes.
those are different objects.
In which sense? From the
Um,
planetesimals?
well, do they make up part of elements that help build the planets?
They do. They do.
Oh, okay.
Yeah, they do. But once they do, once the planet goes through their own evolution, they get mixed up, and then you
Okay.
lose them. Like Earth, Earth was formed out of these chondrules and with carbonates, with with the silicates and all of that. But
Yeah.
once the planet melted, all the original configuration was lost. So you don't have
Oh,
that. You have a
okay.
big mixing now going on. So
Melting pot.
the point is, you cannot find them here on Earth because Earth has changed it. So you have to go to space and find them.
Oh, okay. And they have a different isotope in them.
And they do. They will have a different isotope ratio, and now they take they. It's like when you take a rock here on Earth and you find the ratio between parents and daughter, and then you can trace properties and age of that rock based on that ratio. So now these planetologists, they do the same. They take isotope ratio of certain elements, and by doing so, they can infer how they were formed and what are under which pressure this type of combination or chemical combination can be formed. Um, yeah.
Okay.
All right.
Are you finished recording?
Oh yes, I forgot.